In this presentation, we're going to explore SYCL interoperability with CUDA libraries. Our main learning objectives for this presentation are: learn about the interoperability features provided by SYCL and how we can use them to call CUDA library routines. We're going to learn how to retrieve native CUDA object handles using the SYCL API. And finally, we're going to have a look at code example of calling the cuBLAS Scala routine from a SYCL command group. NVIDIA provides many useful libraries to developers, such as cuBLAS and cuDN. These are widely used as they are highly optimized for NVIDIA hardware. Since migration away from these would require a direct replacement, DPC++ provides interoperability with CUDA libraries. Using the interoperability features provided by DPC++ allows developers to easily call CUDA library functions from SYCL command groups. This is a very useful feature of DPC++. Calling CUDA library routines from SYCL command groups requires a special kind of task called interop task. This interop task takes an interop handler parameter. In regular SYCL code, the command group handler invokes a kernel. The same command group handler is used to invoke the interop task required for interoperability features. In this code snippet, you can see how the interop task is invoked through the command group handler. Note the interop handler parameter to the task lambda function. This will serve an important function later on. Before we can call CUDA library functions, we need to retrieve native CUDA object handles. Currently, there are two ways to do this. We can use methods provided by the interop handler, or we can use the templated SYCL getNative function. SYCL getNative has one limitation in that it cannot retrieve native memory handles. This must be done through the interop handler. With the exception of the above, getNative must define a specialization for each SYCL runtime class which supports SYCL application interoperability. This table shows some of the corresponding native CUDA object handles you can retrieve from SYCL objects. This table is not complete, but shows the most useful handles for developing applications using interoperability features. Let's look at how to actually retrieve these handles using the SYCL API. Here we have created a command group and invoked an interop task with an interop handler parameter. In order to retrieve a cuDevice pointer, we need to call the getMem method provided by the interop handler, passing the accessor that represents the device memory we want to retrieve. In order to retrieve a CUDA context handle, we can use the getNative function with the backend CUDA template parameter. CUDA contexts map to SYCL contexts, so we can retrieve our SYCL context from the SYCL queue and pass that as a parameter to the getNative function. As you can see, the process is the same for retrieving CUDA stream and device handles. Now let's take a look at how we can actually call cuBLAS routines in SYCL and the required setup. Calling cuBLAS routines requires a cuBLAS handle. This handle needs to be created before our queue submission and destroyed after the interop task has finished. This code snippet shows that the handle creation is identical to pure CUDA code. Inside the interop task, we will also need to acquire the native CUDA stream handle to pass to cuBLAS setStream. Next, we will look at a step-by-step example. Firstly, we're going to create a SYCL queue using our CUDA device selector. Next, we create and fill our host vector. Next, we declare and create a cuBLAS handle. Now we need to create a new scope for buffer creation and queue submission. Inside the scope, we create a SYCL buffer from our host data. Now we create a command group submission to the queue. Inside the command group, we create our SYCL accessor. Now we invoke the interrupt task, passing an interrupt handler. Inside the interrupt task, we retrieve the native CUDA stream handle from our queue's CUDA backend. We use this handle to set the cuBLAS stream. Using the interrupt handler, we retrieve the native CUDA memory handle from the SYCL accessor and cast it to the appropriate pointer type. Now we can finally call cuBLAS scal with desired parameters. After you ensure the command group has completed, remember to destroy the cuBLAS handle. You could call myQ.wait before destroying the cuBLAS handle. However, in this example, our buffer is inside the nested scope. This means that once we reach the end of the scope, the buffer destructor will be called implicitly. This is a blocking operation as the SYCL runtime has to wait until all commands using the buffer's data have completed. This slide illustrates the important interoperability components. So now it's time for questions and the second exercise. In the second exercise, you must implement an interrupt task that calls the cuBLAS sgem routine.